Good afternoon, everybody. My name is Mohammad Umar Samara, and I'm going to be presenting our flow over airfoil CFD project with my team members Naveed and Minhaj. So firstly, what we want to do is we want to generate our airfoil. So how we're going to do that is we start a new file, we go on Model Wizard and 2D space dimension. Okay, so now we want to select our single phase flow. So we're only examining laminar flow, so we want to add that to our physics interface. Okay, so we want to study laminar flow, and we're studying stationary flow. So okay, just save the changes. Okay. Okay. Sorry, it just takes a second. Okay. So now what we want to do is we want to build our airfoil geometry. So we go on our geometry and we add a polygon. Okay, so our polygon, we'll call it our NACA 2412. So what we want to do is we want to go on this airfoil generator. Let's just select 100 points, plot that. So this gives us the points of all the of our airfoil to draw our shape. So we want to copy that and put that into this notepad, which I've already done. So we save that notepad file, and we can open this data source as a file. So if I browse it, and I can open it, here, our NACA 2412. Okay, so now we want to build all objects, and this is our airfoil that's been generated. So now we basically want to determine the flow that is in, so like the duct. So what we want to do is we want to go back on our geometry and we want to build a rectangle. So our rectangle, so just to cover the airfoil fully, we'll give it a width of around 1.5, is because it reaches, the chord reaches around 1, so just 1.5 to cover the entire airfoil. And we want to just, so to position our duct, we see that -0.5 and -0.3 and -0.5 work best, since our selection point is the corner. So if we build that object, we can see that our airfoil is covered by our duct. So now what we want to do is we want to go on geometry, and we want to go on booleans and partitions, and we select difference. So we want to add this entire shape to our difference, and we want to subtract our airfoil shape. Okay, so we want to build all objects. So now our airfoil is cut out of this duct. So now what we want to do is we will go on materials, and we're going to browse the materials built in, and we're going to select air. We're going to add that to our component. Okay, that's done. And we're going to basically select this cutout duct to be the air. Okay, so now that's done, and now this is all air. So our angle of attack that we want to measure can basically be shifted like this. So we can change our rotation of the rectangle to be 5. So this gives us a 5-degree angle of attack. This gives us a 10-degree angle of attack. Okay. So right now we just want to study the object at a 0-degree angle of attack. So we're going to keep it at this. So now I'm going to pass it over to my teammate Minhaj.
Okay, so now we'll be setting the fluid properties at the inlet and outlet conditions. So first we'll go to the inlet section and we'll go to velocity and set it as 0.1. Then we'll go to the outlet section by clicking on laminar flow, and then we'll set the pressure as 0. And then we will move on to the mesh and we will select the element size as extra fine, and then we'll click on build all, and we have generated the mesh after this. After this we'll move on to the stationary section and we'll click on compute, and this will take a bit to generate, as you can see. Okay, so now we have generated this, and so now we'll click on surface under velocity, and then we'll click on the color table and select Jupiter Aurora Borealis and reverse the color table. This helps us give a distinct figure which helps us recognize the velocity distribution properly. Now we'll click on pressure and click on surface. Then we'll click on the replace expression section and we'll click on laminar flow and velocity and pressure and select pressure from the section. Then we click on plot. This gives us the pressure distribution.
Okay, now that we're done with the pressure and velocity figures, we would be moving on to the results tab, where we would be choosing the more derived values and then the line integration. And here now we'll be selecting the boundaries. First we select the all boundaries, and then one by one we will get rid of the docked boundaries, so that the only boundaries left would be the airfoils. This process might take a bit of time, but since now we're done, we go to the expressions. We choose the laminar flow as mentioned earlier, the auxiliary values, and from there we extract the stress component. The stress X represents the drag. It represents the drag force, and then the other one, the stress in the y-axis, represents the lift force. And these numbers are recorded in a unit of Newton per unit meter. Newtons per unit meter. And now we can see our values for the following computation. It reads as negative 4.40 times 10 to the power of negative 4 Newton meters for the drag, and negative 2.3699 times 10 to the power of negative 4 for the lift force. And now we go back to the geometry, where we change the rotation angle to 2 degrees and build all objects, and we would be simply repeating the process but with a different rotation angle. We go to the mesh, build the mesh, and now finally it will take some time. Now once we're done with the mesh, we will go to the stationary and we will compute the new results for the new angle of rotation. It might take some time, but finally we're done, and now we would be recording the new values for the lift and drag forces. So we go to the line integration again, and we would erase the previous results, and now the new results are as follows: negative 4.1466 times 10 to the power of negative 4 for the drag, and negative 0.00126667 for the lift force. That's it. Thank you for attending our presentation.